Thank you very much for the introduction, and I would like to also thank all the organizers for being able to speak here. This talk is based on a joint work with András Bezdek, who unfortunately couldn't be here, and Viktor Vig and Ferenc Fodor, who are also organizers of this event, and is from the manuscript stated there. A Planck in the d-dimensional Euclidean space is a closed region bounded by two parallel hyperplanes. The width of a Planck is the distance between the bounding hyperplanes. This is actually known. The famous Planck problem of Tarski from 1932 seeks the minimum total width of n Plancks that can cover a convex body K. And Tarski conjectured that the sum of the widths of the n Plancks sufficient to cover K has to be at least the width of K. And the partial solution was given by Bang, and the problem is already solved as far as I know. And in this talk, we consider a spherical variant of this Planck problem, which originates from László Fejes-Tóth. The parallel domain of a spherical of a great sphere on the of a great circle on the sphere, or a great sphere on the larger dimensional sphere, is nothing else but the parallel. The parallel domain of a spherical radius W/2 of a great sphere on the d-dimensional unit sphere is a spherical zone. So it's basically the intersection of the sphere and the two parallel hyperplanes. For positive integers d and n, let W of d and n denote the minimum width of n zones that can cover the whole sphere. And I would like to note that W and omega is exchangeable during this talk. They mean the same thing. Fejes-Tóth asked, among many other questions, that what is the this minimum width of strips or zones with which we can cover the three-dimensional sphere. And he conjectured that in the optimal configuration, all of the center great circles go through a pair of antipodal points and are distributed evenly. And this result is proved very recently, in the end of March this year, by Jiang and Polyansky. Partial results was earlier due to Rosta for three zones and Linhart for 4. Here we will examine arrangements of equal zones on the sphere from the point of view of multiplicity, where multiplicity of an arrangement is nothing else but the maximum number of zones the points of the sphere belong to in this arrangement. We seek to minimize this multiplicity for certain arrangements and even coverings. It is clear that for n more than d, the multiplicity of an arrangement with n zones is at least d minus 1 and at most n. And in the optimal configuration, which is known to be optimal since the end of March, is exactly n, that is, it is maximal. Frankel, Nagy, and Nassodi last year proved that it is possible to cover the sphere, the three-dimensional sphere, with n equal zones, such that the multiplicity is at most logarithmic. And in a covering, the density and the multiplicity work against each other, so we want to optimize in some sense. Our theorem is, well, first of the theorems is if n is an integer and the sphere is covered by the union of n congruent zones, then each points of the sphere belong to the interior of at most 2 zones, then there cannot be more than 3 such zones. And if there is exactly 3 zones, then this configuration is also unique. We know that it is possible to cover the sphere with 4 or 5 zones while keeping the multiplicity down at 3. And for 4 zones, it's quite easy to see that we can start from the optimal solution of 3 zones and lower the widths so that there are some 2 gons missing, and put the fourth down there. All right, and this configuration can be modified to work for 5 zones as well. A few words about this. we want to show that the covering with at least 4 zones, the open multiplicity cannot be lower than 3, and in the case of 3, there's a unique covering with multiplicity 2. So for this, we are going to need this lemma that every convex spherical polygon with at least 4 sides and an in radius r contains a point which is closer to at least 3 of the sides of this polygon than the in radius r. I'm sorry, I missed that. To prove this, we show that there is a direction in which we can move the center of the inner circle for it to be closer than r to at least 3 of the polygon sides. And it's an important note, this also can be generalized into higher dimensions. So in the higher dimension sphere with these properties, all the zones also need to be spherical simplices. Oh. Mm-hmm. I cannot seem to roll, but it's all right. The previous lemma yields immediately that each spherical polygon determined by the n-central great circles of the zones need to be triangles, spherical triangles. And we consider the graph G determined by the great circles, and there is a quite simple combinatorial analysis about the what we get for n, using the fact that 4 times the vertices equal to 3 times the edges. And we get that n squared minus n minus 6 needs to be equal to 0 for this configuration to work. And the largest real root of this polynomial equation is 3. So there cannot be more than 3 of such zones with this property. For the uniqueness, we will skip the proof now. And we remark that as in the case of this 3-dimensional sphere, this can be generalized to D dimension, as I noted earlier, that with the open multiplicity of D minus is D minus 1, and the great spheres of the zones divide the sphere into spherical simplices. Similar combinatorial analysis as in the previous slide can be stated in this case as well. Let FID of n denote the number of I-dimensional faces of this division. And using the Euler-Poincaré formula, we will get in D dimension as well a polynomial equation of which the largest root, if the largest root of which is n is D, then we are done. And this can be, So this is the conjecture that this is actually true for all dimensions, and it is proved to be true for at the most 6 dimensions, because then the polynomial equation can be solved explicitly, and we numerically checked for up to 100 dimensions, but we highly think that it works in all dimensions. Now, an upper bound for the multiplicity of arrangements. Let alpha be a function with limit 0, and k be a function such that this rather technical condition holds. Alpha will be the width of the zones, and k will be the multiplicity of an arrangement or a covering. Then we can state the following theorem, that for at least 3 dimensions and any real function alpha described above, for sufficiently large n, there exists an arrangement of n zones of spherical half-widths with magnitude alpha n on the sphere, such that no point of the sphere belongs to more than this kn zones. An implicit version of this theorem and the conjecture on the following slide were proved by Frankel, Nagy, and Nassodi last year for 3 dimensions. So this is actually not a theorem, but a conjecture of the previous one, and the priority is the aforementioned authors, if they stated it in the dimension. So for each positive integer d, there exists a positive constant ad, such that for sufficiently large n, there is a covering of the sphere by n zones of half its of magnitude log n over n, such that no point of the sphere belongs to more than log n magnitude zones. As it can be seen, we can guarantee either a covering or an arrangement of bounded multiplicity, but not both together. The proof of the previous theorems uses the probabilistic method of Frankel-Nagy and Nosody, which we modify to work in all dimensions, and we also know that this may also be obtained from the results from the another approach. Following special cases of alpha n for arrangement, if alpha n is n to the power of negative 1 plus delta, where delta is a positive constant, then we can guarantee a constant multiplicity. And if we are not afraid to let delta be even higher, then we can guarantee the practically minimal, or one more than the minimal multiplicity. But these are, of course, not coverings, just simple arrangements. And if alpha n is 1 over n, then the multiplicity we can guarantee is log n over log n with some constant multiplier. And some open questions to finish with. If C of n and d denote the minimum multiplicity of coverings on the sphere with n zones of equal widths, we are curious about whether C is bounded for fixed values or not, or for a fixed d, is this C of n and d even monotone? We don't know that either. And for a fixed d, are there constants that depends only on d, such that for any n, there exists a covering with both the density and the multiplicity not exceeding this constant, so they could or could not be simultaneously bounded. And I wish to wish a happy birthday for the three guys, Ted Bistricki, Gábor Fejestóth, and Endre Makai. And thank you very much for your attention.